In this screencast, we discuss the idea of inverse functions in greater detail. Let's look at example 10.2. Consider the two functions from the previous screencast, namely b equals 22,200 minus 370t, and t equals b minus 22,200 divided by negative 370. Let's look at part A. Draw flow diagrams for each of these two functions. Let's start with the first function. I'm going to begin by rewriting the function as negative 370t plus 22,200. Okay, so for this function, the variable t is the input and the output is the variable b. Well, what happens to t first? When we input t into this function, what happens to t? Well, the very first thing that happens to t is it gets multiplied by a negative 370. After that's been accomplished, the result is added to 22,200. So the very first thing that happens is we multiply by negative 370, and the second thing that happens is we add 22,200, and once that's been done, we get our output b. Now let's look at the second function. The input variable is b, the output variable is t, and when we start with a particular value of b and we substitute it into the function, what happens to it? Well, the very first thing that happens to b is there's a mistake here. This should be 22,200 right there. So when we substitute a value in for b, the very first thing that happens to it is 22,200 gets subtracted from it. So we have to subtract 22,200, and then what happens? Well, the result is divided by a negative 370. So we divide by negative 370. And once that's done, we arrive at our output t. So let's look at b. How do the flow diagrams of these two functions compare? Let's be sure to look at both the mathematical operations that are performed and the order in which the operations are performed. So first of all, let's talk about the differences in the operations that are performed. In the very first function, notice we are multiplying by negative 370, but in the second function we're dividing by negative 370. So we're performing opposite operations with the negative 370. Similarly with the 22,200. In the first function we're adding 22,200, but in the second function we're subtracting 22,200. So the difference in the operations performed between the two functions is that they are opposite. If we multiply in one case, we divide in the other case. If we add in one case, we subtract in the other case. Now let's look at the order in which the operations are performed. Notice that multiplying by negative 370 was the very first step in this function, but it was the very last step in this function. Dividing by negative 370 was the very last thing that was done. Similarly, adding 22,200 was the last step performed in this function, yet subtracting 22,200 was the very first step performed in this function. So for these two functions, you have opposite operations, and these opposite operations are performed in reverse order. So we have opposite operations performed in reverse order. This should make some sense. If you think about starting from t, imagine you had a particular time and you wanted to calculate the balance. The first thing you do is multiply by negative 370, add 22,200, and you get your balance. Now suppose you wanted to work backward through this to arrive at the time again. Well, if I wanted to work backward, that would mean I would start with my b, which takes us here. Now if I wanted to work backward through this calculation, the very first thing that I would have to do is undo this operation. I undo the adding of 22,200 by subtracting 22,200. That gets me past this step. Now I have to undo the first step. How would I undo multiplying by negative 370? Well, I would undo it by dividing by negative 370. So if I wanted to work my way backward to t, that's how I would do it. I would begin by subtracting off the 22,200 that I had added previously, and then I would divide by the negative 370 to undo this first step back here. And that takes me all the way back to the value of t. Okay, let's have a look at part C. Complete the following input-output tables for the two functions. Let's begin with the first table. We have two different values for t, and let's substitute them into our function. When we do that, we arrive at 19,980 for b when t is 6, and 17,760 for b when t is 12. Similarly, when we go to the second table, we're given two different values for b, which we can substitute into our function to determine the corresponding t values. When b is 19,980, we find that t is 6. Similarly, when b is 17,760, we find that t is 12. Before going forward, let's take a moment and talk about the results from these two tables. Notice if we start with 6 and we substitute it into our function, the function turns the 6 effectively into 19,980. If we take that 9,980, which appears in this table, and we substitute that into our inverse function effectively turns this 19,980 back into the 6 that we started with. Similarly, if I start with t equals 12 and I substitute it into my original function, I arrive at an output of 17,760. If I take that output of 17,760 and I substitute it into my inverse function, the inverse function takes that value and returns the original t value of 12. When you compare the flow diagrams for the two functions above as well as the input-output tables, you can see that the two functions describe inverse processes. One function effectively undoes what the other function does. The result is that the input and output variables for these functions are reversed. In general, we can describe the relationship between inverse functions as follows. If two functions f and g are inverses of each other, and you know that f takes an input of x and outputs a value y, then the function g must be able to take that output of y and return x back. In order to make sense of this, you have to recall how function notation works. Remember that whatever value is in the parentheses that refers to the input of the function. So in this case, if I take a function f and I input a value x, this equation says that my output is a value y. So if I substitute a value x into this function, I get a value y out. And then if I take my g function and I look at this equation says that if I put the value y, namely this value right here, if I take that value of y and I put it into the g function, which means I'm doing this, then the g function, the output of the g function is going to be the x, this x, back again. In other words, the g function will take the value of y and it will return x back. So you can see from this picture that if x, y is an input-output pair for the f function, then y, x will be an input-output pair for the inverse function. Graphically speaking, this would mean that if x, y is a point on the graph of the f function, then yx would have to be a point on the graph of the inverse function. Let's go ahead and look at our next example where we will get to practice some of these ideas. Let's look at 10.3. Consider the function y equals 2x minus 1. Part A. Let's determine the inverse function. So we need to determine the function that has the opposite inputs and outputs of this function. And we can do that by taking this function equation and solving for the input, which in this case is given by x. So we will start by solving for x. So we have y equals 2x minus 1. We can add 1 to both sides. That will give us 2x equal to y plus 1. And to get x by itself, I would divide both sides by 2. And if we do that, we arrive at x is equal to y plus 1 over 2. So this is the inverse function right here. So our original function was y equals 2x minus 1, and our inverse function is x equals y plus 1 over 2. These two functions describe inverse processes of each other. Now let's have a look at part B. Write your function, in other words, the inverse function, in the form y equals mx plus b. In other words, we're going to use the letter x to represent the input of the function, and we're going to use the letter y to represent the output of this function. Okay, this may seem a little strange to you at first, but remember that when we first talked about functions, we said that the choice of letter names for the input and output variables never matters. So for example, if I went up to my original function, I don't have to use the letters x and y for input and output. I could have used r and s, or t and q. The choice of letter names never matters. Remember that the function is the process that turns inputs into outputs. What you decide to call the inputs and outputs is irrelevant. So for our inverse function here, right now the letter y is playing the role of the input and the letter x is playing the role of the output. But we don't have to call the input y and the output x. We can call them whatever we like. We often, in algebra courses, use the letter x to represent the input of any function, and the letter y to represent the output of any function. Well, this is a function in its own right, and we can use the letter x to represent the input of that function and the letter y to represent the output. And if I did that, we would arrive at y equals x plus 1 over 2. Now notice that the process is still the same. Notice this formula is still the same as this one. This process and this process are still reverse processes of each other. I'm just simply using the same letter x in both cases to represent input, and I'm using the letter y in both cases to represent the outputs of these two functions. But I can't emphasize this enough. The input-output pairs of this function and the input-output pairs of this function are still reversed from each other. They're still reversed. Okay, there's one last thing to do. We were told to write our inverse function in the form y equals mx plus b. Well, we have our inverse function written in the form y equals, but now we need to work on the right-hand side of our equation so that we're writing it in the general or the standard equation for a linear function. We can do that by taking our current equation. The right-hand side is one large fraction, which we can split into two smaller fractions. And we can rewrite the first fraction as 1 times x over 2 plus a half, and the first fraction then can also be written as 1/2 x plus a half. So what we have now is our inverse function written in the form y equals 1/2 x plus a half. So it has the form right now y equals mx plus b. So we've accomplished our goal. Okay, now let's have a look at part C. Carefully sketch the linear function y equals x along with the inverse functions y equals 2x minus 1 and y equals 1/2 x plus 1/2. Recall, these were the two functions that we were studying on the previous page. You can see now why we would want to rewrite our inverse function with the letter x as the input and the letter y as the output, because what we're going to do now is graph these two inverse functions on the same axes, where x is the variable representing our horizontal axis and y is the variable representing our vertical axis. So we need to use the same letter x for the input of these two functions. So let's start by graphing the function y equals x. Well, y equals x, I can rewrite that as 1 times x plus 0. And this, if I write it in this form, it is in the mx plus b form. So you can see that this particular linear function has a y-intercept of 0 and a slope of 1. So in other words, it crosses the y-axis at 0. It has a slope of 1, which means every time x increases by 1 unit, y also increases by 1 unit. So this graph will go through 1, 1, 2, 2, 3, 3, etc. So the graph will look like this. So this is y equals x. Next, let's look at the graph of y equals 2x minus 1. 2x minus 1 has a slope of 2 and a y-intercept at -1. So this is a function whose graph crosses the y-axis at -1, and the slope is 2, which means, as you'll recall, 2 is the same as 2 over 1, which means every time x increases by 1 unit, y increases by 2. So if I start at my y-intercept and I go 1 unit to the right, I climb 2 units, and that puts me at this point. If I start from that point and I go 1 unit to the right and I climb 2 units, I end up at that point. And if I keep going, 1 unit to the right, 2 up, I trace out a line. So this line looks like this. So this is y equals 2x minus 1. Now let's look at the last line, y equals 1/2 x plus 1/2. You can see here m is a half and b is also a half. So this line crosses the y-axis at a half, should be about there, and the slope is 1/2, which means that whenever I increase x by 2 units, y increases by 1. So if I start from my y-intercept and I go 2 units to the right, the value of y has to climb by 1 unit, so I end up right here. If I start there and I go 2 units to the right and 1 unit up, I arrive at this point. Again, go 2 units to the right, 1 unit up, and you arrive at this point. So this line looks like this. So this is the line y equals 1/2 x plus a half. Now let's look at part D. Your work in part C illustrates that graphs of inverse functions are mirror images of each other across the diagonal line y equals x. Well, let's go back and look at that. So this line right here, y equals x, is referred to as the diagonal line, always. This line right here makes a 45-degree angle with the vertical axis, and therefore it's called the diagonal line. And if you look at the graphs of the two inverse functions, you can see that the picture, you can imagine having a mirror right along this line. And what you see on one side of that line is the mirror image of what you see on the other side of that line. And that will always be the case with inverse functions. When you graph them, they will always be what we call symmetric about the line y equals x. In other words, they will be mirror images of each other across this line. Why do you think this should be the case? Well, the answer is actually a bit complicated, but I think we can begin to see why this is probably the case by looking at some of the points that these graphs go through. So, for example, if we take this point right here, the coordinates of this point are 2, 3. So 2, 3 is an input-output pair for this function. 2, 3 is an input-output pair for this function. And notice that right here, this is 3, 2. That's a point that is on the graph of the inverse function, and you can see that the input-output pairs are reversed from each other. These 2 points here are mirror images of each other when you are looking at the diagonal. These are directly opposite of each other when you look across this line. Similarly, if we take the point right here, this is the point 3, 5, And if we look over here, this is the point 5, 3. Again, the input-output pairs are reversed from each other, and these 2 points are really on opposite sides, exact opposite sides of the diagonal. So the fact that the input-output pairs are reversed from each other is what creates this mirror image that we see in the graph. So why should this be the case? I'll just say real briefly, it's due to the reversed input-output pairs. Okay. So far, all of the examples in this chapter have involved linear functions. One of the lessons that you can take away from this section is that inverses of linear functions having non-zero slopes are again linear functions. So an obvious question to ask is, what about other functions? In the next section, we'll look at inverses of exponential functions. In the final section of this chapter, we'll briefly talk about other functions. But for right now, the takeaway message from this particular section is that if you start with a linear function that has non-zero slope, the inverse is going to again be another linear function with non-zero slope.